All right, here we go. So, for those of you who are following along at home, this is the Chapter 7 examples, which can be found in your Week 11 folder for Online Statistics 1. So today we're going to talk about the normal distribution, which is something that we're going to be using on and on and on as this class goes on to calculate some things. And it's something that shows up a lot in Stat 2. So if you're going to be taking that class, I suggest you familiarize yourself with this. So this first question I've got is about the adult IQ scores, which are normally distributed with a mean of 100 and a standard deviation of 15. And we're going to use the 68, 95, 99.7 rule to figure out a couple different things about the IQ scores. So we first note that since it's normally distributed, we can use the 68, 95, 99.7 rule on it. And the first thing I'm actually going to do is I'm going to go down here to the distribution and fill out the distribution values to make it a little bit easier to calculate these values. So I know so far, I'm going to try to fill this in right below it. There we go. I know the mean is 100. And then I know if I add one standard deviation to that, I'm going to take 100 and add 15 to it, and that'll give me 115. And then if I add two standard deviations to that, I'm adding another 15, so that's 130, falling at the second standard deviation away from the mean. And then the third standard deviation away from the mean will be adding another 15, so that'll give me 145. Now I'm going to go through and do the same thing on the other side, but with my subtractions. I'm going to have to be a little careful with this one because my distances are going to get weird with the spacing on Word. Okay, so first up, if I subtract 15 from 100, I get 85, and that gives me my first one standard deviation to the left of the mean. Oh. If I subtract two standard deviations away from the mean, I'm going to subtract another 15 away from 85, and that'll give me 70. Looking good so far. And if I subtract a third standard deviation away from mean, I'm subtracting 15 from 70, or 15 three times from 100, which gives me 55. Okay, so as I'm looking at this gives me a lineup for what everything is happening here. Now, a couple things to keep in mind when you're looking at the 68, 99, 95, 99.7 rule is that, remember, the normal distribution is symmetric, which means as you're looking at this, what happens on one half also happens on the other, so you can reflect and double up things if you need to. That means you also, when you know that this is 68, you can have it and get that this little section here is 34%. This little section here is 34%, and so on and so forth. So this 13.5 here came from taking 95, dividing it in half, and getting 45.5, and then subtracting from it the 34 to give you that little section, and so on and so forth with the rest of these too. Alrighty, so we're going to use this fact. And the other thing we want to keep in mind is the law of total probability that tells us for the normal distribution, and any probability distribution tells us that the total amount of probability here must be 100% and or 1 if we're thinking about probabilities instead of percentages. So in total under here I have 100%, which means that when I divide this in half and look at this half of the graph, everything in here, that should be 50% of my scores, and this half of the graph should be also 50% of my scores. So if I'm looking at what percentage of IQ scores fall between 85 and 115, that's from 85 to 115. That's one standard deviation in each direction, which from the rule tells us this is going to be 68%. Okay. Next up, we want to look at scores that are greater than 130. So there's a couple different ways you could do this. If you look at my solutions, I did it using these percentages that are here, but I'm going to do it a little bit differently this time. So I know that 130 is two standard deviations away from mean, which is 95%. Which means that I'm outside of that, so I'm looking at things that are not a part of that 95%. I'm looking at 5%, which would be this tail and that tail. But if I then want just one tail, I should half that. So that would be, 2.5%. So there's another way for you to think about this. So again, I know that between 130 and 70 is 95% of all scores. So outside of those two should make up 5%, which would be this tail and this tail. And since it's symmetric, if I want just the upper half of that, I want half of those scores, and therefore I want half of 5%, which is 2.5. All right. Now let's do from 100 to 130. So I'm looking at the scores between here and here. So I can use what I just did in noting that this tail that's left over of being above 130 is 2.5 and subtract that from 50%, since I know the total area under here is half of the distribution, which is 50%. And that will give me the 47.5. And that's one way to handle that. The other way you could do this is you could take the percentages that are already present on this normal curve and say, oh, well, if that's 34% and that's 13.5%, and I want the area between here and here, I can just add those together, which is also 45.5. Okay, and if I want the middle 95% of scores, that's going to be 2 standard deviations away from mean, so that's scores between 70 and 130. All right. Let's do this again, but now we're looking at a slightly different distribution. So we're still looking at something that's normal, but remember all these have the same shape. It's just a matter of scale and center. So our center is our mean at 500, and our scale and or our distance and or how we describe the spread of this distribution is about 100. So I'm going to get below this. Hold on. Oh, I was really hoping it would let me. I'm going to change some of the spacing here so that I can fit a couple things in below my graph. There we go. Or not. That's going to go well. Okay, so if you somehow can manage to fit this in here, crapola. I'm just going to fix the spacing. You're spending 10 minutes watching me play with Word instead of figuring out how to do this. It's awesome. Not really. Okay, so hopefully we can go through this exercise okay and it won't be screwy looking. Nope. Just move that up a little. Okay, that's the opposite of what I wanted to have happen. Darn it. Okay, so yep, it'll be cool. So the center is 500, and then going up every 100 gives you, yep, just going to do that for now. So our center is 500, which means 1 standard deviation up will be 600, and then 2 standard deviations up will be 700, and then 3 will be, or 7,000 for a fun time. Will give us a 800, and then if we do the lower end scores, that will be 400, 300, and then last but not leastly, 200. Okay, so I'm going to try moving this down a little bit now. Oh, that lined up so nicely. I'm having a good time today getting this. Oh, I finally got it. Okay, that's probably way loud on the speakers. I am so sorry I did that. Okay, so let's say I want to know, hey, how do I score among all students who took the SAT if I got a 600? So if you scored a 600, usually we describe students scoring and how they behave by using what are called percentiles. And I'm hoping that you remember that we always kind of do this in the egotistical way of I want to know how how many people I did better than. So I look at all the people in the tail, which would be, all the people not in this side. So here you could do this as I'll take 64, which is this percentage, add the 13.5, add the 2.4, and then add the 0.1% that's in there. And if you do that, you get 84. So you're in what's called percentile 84. And usually we do this as a subscript, which just represents that you scored better than 84% of all people who took the test. One thing to keep in mind when you approach this is scoring a 600 and scoring less than a 600 or less than or equal to a 600 look exactly the same for this distribution and for any distribution, because when you're calculating how many and who, you're accumulating values. In order to do that, you need area. So when we're doing this, we are adding up areas. And if you look at a single value like probability of being 600, this is very different from the binomial and the geometric, in that there's no area below a line. So they're having an equal to here doesn't matter. So what I'm saying is that the probability that you're less than 600 comes out the same as being the probability that you are equal to 600. Okay, so What percent of SAT scores are between 400 and 600? Oh, look, we're one standard deviation away from the mean each direction. That's going to be 68%. Okay, and what percent of students scored above a 700 on the SAT? So I want above the 700, so I can take this 0.24, or sorry, 2.4% and this 1% and add that together and get 2.5%. So if you're having a hard time with this, one of the things I would suggest is that you redraw the distribution every time and then color the area you're interested in from the probability statement that you're trying to discover, and then divide this up and decide whether or not you can calculate that using this 68, 95, 99.7 rule. And as we'll see, that's not always the case, unfortunately. You don't always necessarily fall exactly on a standard deviation. And when that happens, you need z-scores and/or you need Minitab. So if you've been wondering why I have this left panel here this whole time, right? Yeah, of course you have. Okay, so let's look at the standard normal curve. So in case you forgot the standard normal curve, we usually symbolize with this n, and we say that he has mean 0 and standard deviation 1. So if you imagine the mean being present on these graphs, it falls right at 0, falls right at 0. And what I want to do is I want to calculate some probabilities. So I'm going to show you how to do this on Minitab two ways. One of the ways I'm going to show you handles situation B very well and not so much situation A. And then the other way will handle both of these equally well. So I am very preferential on this. One of them I like a lot better because it always gives me a picture, and for those of you that are visual learners, that will work out a lot better for you because you'll be able to connect the picture with what you were thinking. And so, you know, there's that. So we're going to first go up to what I call, well, this is the first one, just so you know. I'm going to do B first. So I'm going to go to graph and then probability distribution plot. This one's the one that's my favorite because it always produces a picture for you. And then we're going to choose view probability. So again, those steps were graph, probability distribution plot, and then view probability. In this class, we won't be using any of these other ones, so don't worry about them so much. We're going to hit OK. It has a lot of distributions in here. We want the normal distribution. Notice it gives you an option for the mean and for the standard deviation. When we get to number 4, notice we're going to be dealing with a different mean and different standard deviation, and this will be nice because I won't need to turn it into z-scores first and look anything up on a table. I'm just going to be able to put in the mean, put in the standard deviation, and just go crazy. Well, not literally go crazy, but you get the idea. So what I want to do is I want to look up a score and look at the probability to the left of that score. So you notice how there's this second tab up here called shaded area. That's how we're going to tell it what area I want and what I want off of that area. So I'm going to click here, and it's automatically going to be set to probability, and that's if you know a probability and you want to know a score that goes with it. We don't have that. We have a score and we want to know the area. We want to know the probability. So I'm going to hit X value, and notice I've got all these options. Do I shade towards the right? Do I shade towards the left? Do I have 2 of them, or do I have something in the middle? See how this is going to be useful for part A? I know I'm doing B first. It's so awesome. I am dealing with a left tail situation because I'm going to be shading to the left of negative 0.38. And that's all I need. I'm going to hit OK, and it's going to produce a picture for me that'll show me exactly what's going on. Ah, do you like it? It's kind of fun, right? Maybe. So there's your probability right there. It shows up usually somewhere above the little area piece that you found. Occasionally it'll show up in it, but not often. You can just pick it up and move it like I just did, if that happens. So for A, and I'm even going to write this as for B, I'm going to write this as a probability statement. This is the probability that Z, not X, because this is the standard normal, is less than negative 0.38. is equal to, and I got 0.3520. Okay, and I'm going to show you a second way to do B. So other than the probability distribution plot way of doing this, there's also the option to use the calculate menu, which has probability distributions on it. In particular, it has the normal. So I'm under calculate, aka the calc menu, probability distributions, and then normal. We're going to select this, and you have to go through some similar options. So for this one, it will only do area to the left. So it'll only do situations like B. It will not do situations like A. Sad but true. Okay, so it starts with the standard normal distribution, If you want to do a different distribution, you'll have to change the mean and change the standard deviation. It gives you an option to input a column of information if you wanted. So if you had a lot of scores you wanted to do at once, you could enter them into this column by typing them in and then telling it which column you wanted it to do and where you wanted it to store it. We're not going to do that. We're just going to do a single value. So I'm going to choose input constant to get a single value. So I'm going to put in negative 0.38. Notice I didn't put the 0 in this time because it won't make a difference. And if I want, I can choose to store that in a column, but I don't want to. I'm just going to get an output. Oh my gosh, I'm sorry about the yawn. If you hit OK, then in your session window, what shows up is the actual probability. Now, if you look at this versus what I got from the probability distribution plot video, or sorry, picture from over here, it is slightly different. The one coming off of the calc menu is always a little bit more accurate. It always gives you more decimal places. So if you're doing some really, really fine calculations where you're really, really worried about your area, it's important that you probably use that one to get your probability, because unfortunately the one with the plot always rounds a little bit, and it always rounds to 4 decimal places. So if you're really worried with what you're doing and your business client needs something very detailed, or you're dealing with tiny things like small engine parts, you probably should do the more detailed version. Okay, so let's do A. I'm going to show you 2 ways to do A again. So the easy way is to use my first method, which is graph probability distribution plots. We're always going to choose view probability, no matter how much it wants us to do view single. I'm still on normal, still mean 0, still standard deviation 1. Only now I'm going to choose middle, because I'm doing in between 2 values. So my lower value I have here is negative 2.48, and then my other value, my other x value, is negative 0.58. So lower, upper. Here we go. We'll hit OK. And there's our picture. So here I've got that the probability that I'm between negative 2.48 and negative 0.58 is 0.2744. Okay. Now, if I wanted to do this using the calc menu version, I actually have to separate it into 2 probabilities, because it only does probability to the left. It only does less than or equal to, so you can't make it go the other way. So what I would do instead is I'd calculate the probability that I'm less than negative 5.8. So that would be all of the stuff to the left of it, and then do the probability to the left of negative 2.4, which would be all the stuff in this little tail, and then subtract them from each other. So it's basically like, instead of doing the middle area, I'm doing left and then minus the stuff I don't need, so that I get the stuff in between. So instead we're going to do the probability that z is less than negative 0.58, and subtract from it the probability that z is less than negative 2.48. So I have to do 2 calculations and subtract them from each other. It comes out exactly the same, so you can literally pick whichever one you want. So, you know, just so you're aware, a little bit of a difference on that. So we'll go up to calc, probability distribution, normal, and here I'm going to be inputting the constant. Let's do the negative 0.58 first, and hit OK. So that value would be 0.280957 minus, and now I need to go up and do it again. So we go up to calc, probability distribution plot, and normal. All my stuff is the same except for I need to put in the negative 2.48. Do I have a negative in there? Yes, I do. And then I just need to hit enter, and that gives me my second probability, which is 0.0065691, and you'll watch this will give us something slightly more detailed, but you know, sometimes you need that, sometimes you don't. I'm actually entering this into a calculator as we speak. So I got 0.2743879. So again, slightly more accurate, but good enough. So if you only need 4 decimal places, you know, there's no point in doing the extra work, but in case you want to know, there you go. All right, now let's do that again, but let's do it with the SAT scores. So we're going to pull up, and since this is looking at falling between two values, I'm going to use the graphical version because it's going to do a little bit of a better job here, and it's a little faster. So I go to Graph, Probability Distribution Plot, Probability View. I'm looking at a middle two values. Now my mean is different here. My mean is 500, and my standard deviation is 100. I'm going to go to Shaded Area, and again I want middle. So my lower x value, always put the lower on the left, is 450. Ooh, 4,500, that'd be bad. And then my upper one is going to be 600. We're going to hit OK. And look at that. Nice and easy, nice and cheesy. So that value is 0.5328. I'm going to format this a little so that it matches my above answers, and that's easier for you to read, I hope. I'm going to zoom in a little. There we go. That's a little bit nicer. Yep. So now let's do that again, but let's look at between 520 and 600. So we should expect this to be smaller because I'm including less values. So I'm going to go to Stat. Or sorry, I keep saying Stat. We're doing statistics, so I want to hit Stat. Graph, Probability Distribution Plot, Probability View. And doing between values is just so much easier using this version, and it's going to be so much faster when you go to do your homework too. So between 520 and 600, let's hit OK, and there it is, and it is smaller. Notice that this sometimes happens where your graph gets a little crushed. You can actually make it a little bit bigger to avoid that problem. Oh, but it didn't matter. Oh, my screen's not big enough to fix this, I don't think. It's not. Yay! Okay, so our probability for this one is going to be 0.2621, and that makes sense. It sort of is, it's less than a 1 standard deviation away from the mean, which, you know, the mean falls right about at the center. Well, it is at the center. And that would be 34%, so this is slightly smaller since it's not that entire first standard deviation away from the mean. Okay, now I've done two centers because I'm looking at values between two. Now I'm looking at things that are being scored below 400, so this is going to look different. So I want to look at stuff that's less than 400, so this is going to be a left tail. So we go up to Graph, Probability Distribution Plot, Probability View. It's going to bring up my last mean and standard deviation. Since I'm still dealing with these SAT data, that is perfectly appropriate. I'm going to go to Shaded Area, and instead of doing two values, I'm going to choose left tail and change that to a 400. Woohoo! Okay, and there's our graph. So we just discovered that that's 0.1587. Alrighty. Alright, so last but not leastly, we're going to do D, which is I want to look at the top 10% of scores. So I want to figure out which score marks 10% of area. So, oh my gosh, I need to get more sleep. So what I'm looking for is I want to find the top 10%. So I want to find the score, so the X value, aka the SAT score, that represents the top 10% of scores. So, you know, I want to find the value that has 10% area. So I'm doing the opposite problem. So far we've taken scores, figured out the area, used that to do probability. Now we're going to take area and then, you know, treat it as a probability, because that's what it is, and then use that to find a score. So we're going the opposite way. And you can still do that. It's pretty easy to do. I'm going to go back to Probability Distribution Plot, Probability View. I'm going to keep the same mean and standard deviation so that I can do this in one step. I'm going to go to Shaded Area, and notice there's the option to choose probability, so I can enter a probability into here. We do want that. Okay, I want 10%, which, remember, probabilities are decimals. Please don't forget this. You should only change them to percentages if you say percentage in the problem or it says report your answer as a percentage. This is really going to be a difficult point in your homework as you go through. If it says report your answer as a percentage, then you should be using percentages. If you've been paying attention, I've been only using decimals for these because that's what probabilities actually are. They're proportions, they're fractions, they're decimals. Okay, enough off of my high horse of things that are happening. So top 10%, right tail, that'll give me the top part being 10%. So notice it has a little P here marking out where your probability would be. So there's like a slight little change that happens between clicking between X values. So it's like marking the X's down on the bottom and clicking on probability where it marks the P's because you're actually looking at probabilities instead. All right, let's hit OK. And there is our score. It appears that you need to score a 628.2. Oh, I missed a 2 in there. Sorry about that. Or better. But I'm hoping you remember a little bit about the SAT. If you don't, that's okay. You can't score a 0.2 on the SAT. You can't get 2/10 of a point. And you also can only earn them in multiples of 10. The test only allows you to score 10 points at a time. So really what we need to do is we need to say that it's, 630 or better. But if you didn't know that about the SAT, that's okay, because it's not like all of you will take that. A lot of people will take the ACT instead. So, just keep that in mind. It's not just, random calculations. These have more to them than that. You should always think of your numerical values as not being just flat numbers. These have context and meaning behind them. Alrighty. So, let's look at dealing with some tires. Wow, this is longer than I realized. Whatever. So let's suppose you're looking to buy some snow tires, and you know that they're normally distributed in their mileage that they'll handle, and they have a mean of 32,000 miles and a standard deviation of 25,000 miles. And if you select a set of those tires, you want them to last like 40,000 miles or more, but that's not very likely. Since only 7% of all tires will last longer than 40,000 miles, is it reasonable to expect that yours will? Well, okay, let's be honest. Like, absolutely not. Let's confirm that calculation is correct real quick. So let's go up to graph, probability distribution plot, the probability view. I want to change my mean to 32,000 and my standard deviation to 25,000. And I want to know the probability that I'm going to last longer than 40,000 miles. So notice I'm doing area to the right because I want it to last greater than that. Okay, this is pretty unreasonable because you should see that that's a small standard deviation, and 32,000 and 40,000 are pretty far apart, so it's probably not going to happen. Let's hit OK. Look how tiny. Oh, look how tiny that is. I'm going to move the p-value a little bit so you can read it. It is less than 7% of the time. Yeah, so I'm going to go with, it's not reasonable to expect this. No. It is highly unlikely that your tires because if you look at this, a tire that will do this will be about like 6 out of 10,000. That's just not very likely. And here you're looking at 4 of them, so it's just not bloody likely. Okay. So the next thing you might want to ask yourself is, how likely is it they last less than the average time? So how likely is it that you might end up paying a rebate? Or you might be getting new tires because they didn't last as long as they were warrantied. So we'll go to graph, probability distribution plot, probability view, and look at doing less than 30,000 miles. And this should be quite a lot of them because that's just shy of the mean. Oh, it looks like 0.2119%, or if you like the percents, okay, 21.19%. That's not very good. Okay. All right. How many do you think will last between 30 and 35,000? So I need to do a between one now. Ooh, graph. Oh, where is it? Oh, probability distribution plot. Probability view. We're going to hit OK. Same mean, same standard deviation. I want a middle, and I want between 30 and 35,000. There we go. Let's hit OK. Well, that's quite a bit of them, and they are both right around the mean, so that seems pretty likely. That it be a higher score than what you might expect, so 0.6731 or 67.31%. Notice I'm writing or here because these numbers are absolutely not the same. Please don't write that these are equal. You should know in your heart of hearts that 67 is not the same number as 0.67. Just throwing that one out there. I see people write these crazy things all the time. Yay, the joys of math. Okay. Let's look at mileage guarantees. So what I want to have happen here is I want to have, 1 out of every 25 customers to be given a refund. And that's it. I don't want it to be more than that to save myself some money. So 1 out of 25, in case you didn't know, that's 0.04. So that's the probability I'm interested in. I need to find the score that acquires that. So we're looking for the mileage or less that we want to offer retail, not retail, sorry, rebates for. So what we're looking for is a cutoff value for how high I should go. So we're going to go to graph, probability distribution plot. I'm still doing probability view because that's the one I like, and that's the one that gives me a picture and definitely helps. Still the same mean, still the same standard deviation. I'm going to click over to shaded area. And here I'm given a probability, not a score, so that's what I need to put in. And I'm looking to find the score that has 0.04 to the left of it because I want to be able to make sure that I'm not giving people that have above that mileage a rebate, just that mileage or lower. So this is going to be a less than or a left tail. Is that okay? So it looks to be, so we want people whose tires last less than 26,623 miles. But let's be honest, most people will round this to 26,000 just because it's a nice round number and easy to report. So there you go. Alrighty. Let's look at some babies. Well, okay. They're 3-year-olds. I don't know what I'm talking about. It's fine. They're small children? That's more accurate. Okay, so suppose you have the height of 203-year-olds, female patients, and the heights are normally distributed with a mean of 38.7 inches and a standard deviation of 3.2 inches. If one of these patients is selected at random, find the probability that the patient will have height of less than 32 inches. So we're going to assume this is relatively normal because it's a large sample size, and we know the mean, and well, they tell us it's normally distributed, so it's appropriate to use a normal model for this. I know the mean, I know the standard deviation. What I want to know is I want to know the probability that this person is less than 35 inches tall. So as you look at this, this is clearly a left, since it's doing a less than. Ooh, sorry. So I'm going to do a probability distribution plot, probability view, and I'm still dealing with a normal. I need to make my mean accurate. So my mean is 38.7, and then my standard deviation is 3.2. And then I'm going to go to shaded area. I'm no longer dealing with a probability. I have a score that I'm interested in, and I don't have a middle. I want to know the likelihood that I'm less than 35 inches tall, so I need to change this to 35. Watch your units on this. If you get something that's in inches or feet, or sorry, if you had this in feet and then all of these were in inches, you'd need to convert first. That's a really common tactic to confuse people. Don't forget about doing conversions. They should all be in the same units in order for this to work correctly. Let's go ahead and hit OK. It appears that only happens about 12% of the time. Alrighty. Next, let's find the percentile rank of a 3-year-old who's 43 inches tall. So remember, percentile is your score or worse. So again, I'm looking to the left of 43 inches. I just had to explain to my mother-in-law that her cholesterol score was reported, and this is really common. Doctors like to report things with percentiles, especially when it comes to medical testing. And hers was, by age group and all this stuff, and then there was this percentile there, and she didn't know what it meant, and so I got to use statistics to explain to her what her medical test went and how she should stop eating so much salt, which I doubt she'll listen to me. Why am I telling you this? I'm talking to no one right now. Woohoo! Okay, so again, we think of percentiles as who you scored better than, so in this case that's people that are shorter than 43 inches, so I'm still doing to the left of 43, and then we'll hit OK, and so 91. We get 0.9105. So I would say that she is in the 91st percentile. Woohoo! Yep. Okay. Let's find the probability that a patient is between 35 and 40 inches. So we're going to go up to graph, probability distribution plot, probability view. I bet you're sick of me saying that. Hit OK and do the shaded area. Notice my mean and standard deviation are staying the same because I'm still in the same problem. I want to do a middle now, so I want to do between 30 and 40. Occasionally, just as a warning, 35. If you try to put something larger here than you do there, it gives you an error. So just try to keep in mind it goes in order. So we count numbers in increasing value from left to right. So make sure you always put your smaller one in value 1 and your larger one in value 2. We'll hit OK. Woohoo! Got lots of graphs today. Oh, it's about half. Well, a little bit better than half, so 53.39%, or 0.5339. Woohoo! All right, let's find the 20th percentile. So lower 20%, upper 80%. This is where my niece was when she was 3. She was tiny. Sometimes I pick these numbers from fun places. Okay, so let's look at graph, probability distribution plot, probability view. We're going to hit OK. And here I'm looking for scores that are in the lower 20% or upper 80. You can do either. In fact, for fun, maybe let's do both. But I'm not looking for a value and finding a probability. I'm given a probability and looking to find a value. So I'm looking at the left tail and I want to find the lower 20%. Let's hit OK. Alrighty. So it appears about 36 inches tall. If you want to be more accurate, I am perfectly okay with you doing 36.01, because believe me, if you're 36 inches tall, you're going to count that 01, just like how children count half birthdays. So, alrighty. Okay. Let's talk about ACT scores next. So I did the SAT, got to do the ACT. Also, East Coast, West Coast, all that jazz. So the ACT is scored on a totally different scale from the SAT, in case you didn't know. The first time I took the ACT, I was violently ill and did terribly. And then someone told me you should always take standardized tests at least twice, because I shouldn't say 100% of the time, almost every time people do better on their second try. So you just have a better feel for the test. So if you did bad on your test, it's not a bad idea to retake your standardized tests if you're looking to get into a better school. The same thing is true for those of you looking to take the GMAT or the GRE. So my mean is now 21. My standard deviation is 4.8. See, totally different scale. But we can still use z-scores and probability to figure out what's going on, since they're both normally distributed. So I'm going into graph, probability distribution plot, probability view. Believe me, at this point, you'll probably have this memorized. Let's hit OK. All right, I'm going to change my normal to being 21 as the mean, because that's the mean of the ACT distribution. And then a 4.8, because that is the standard deviation of the ACT distribution. Let's go to shaded area. Oh, I didn't even read my problem. Oh, what am I thinking? Oy, oy, oy. Okay, if one ACT score is randomly selected, find the probability that it's greater than 25. Okay, so I want to do an x value and find a probability, and I want to be greater than 25. Let's hit OK. And there we go. So about 20% of people will do this. All right. Now we need to find the scores that are less than 19. So go up to graph, probability distribution plot. Since this is going to be a less than, I'm going to be looking at a left shaded area instead of a right this time, and doing 19. Let's hit OK. There we go. So scoring less than a 19, unfortunately, that seems like it's a lot of people. 33.3385. That's sad. Okay, how about between a 26 and a 30? It's a pretty good number. Graph, probability distribution plot, probability view. Oh, and I'm looking between two scores. So I want some middle action here. I want to be between 26 and 30. I'm getting a little fast at these. I should slow down. Breathe. Calm down. Okay. Boy, it's just running out of places to put my graphs. So about 11% of people will score between a 26 and a 30. That's a pretty good score, actually. You should be pretty proud. Let's say you score a 30. Now this is like typical what people want to know is, I want to know what my rank is. Percentile rank, remember, is always doing the percentage of people you scored better than. So I'm going to be doing a left tail here. So graph, probability distribution plot, probability view, and then I'm looking to the left of the score that is 30. Let's hit OK. Oh, it's all the way down here. 96. So this percent is going to be 0.9696. So we would probably call you the 97th percentile by rounding this a little because it's just that darn near close. So we'd say the score is in, or I should say their score. English, it's important. Is in the 97th percentile. I would usually write this as in the 96th because they're in the 96th, not quite in the 97th, but let's be honest. When you're trying to inflate your scores and talk to your friends about your ACT, you're like, I scored in the 97th percentile. You should go use your math skills to find that out, like what my score was, and then you'll see why you scored better than them because they won't be able to figure it out. Or don't be a butthead like that, and I tried to find an appropriate word to say and came up with butthead. That's not good. Okay. So we also represent that as a capital P with a little 97 to represent the 90th percentile. So now I want to find P80. Wahahaha. So I want to find what score is the cutoff so that 80% of all scores are below you. So let's go to graph, probability distribution plot, probability view, and here I want stuff to the left, but I want probability view, not x's. So I want the lower 80%. Where is it? Ooh, it's a 25.04. So we'd probably report this as a 25 because you can't score a 0.04 on the ACT. Cool. Now, here's a really fun question. This is probably my favorite one on this page. What's the IQR? Okay, so hopefully you remember the IQR is quartile 3 minus quartile 1. So how do you find the quartiles? Well, remember quartile 3 is going to be the third quartile. So, okay, how can I describe this? The first quartile, remember, your second quartile is the median. That marks the place where you split it into 50% and 50%. And then quartile 1, so imagine like taking this, cutting it in half. So there's the lower half, there's the upper half at 50. And then quartile 1 splits that in half, so it represents 25% below and then 75% above. So we think of quartile 1 as being P25. Sorry, I hit the decimal point on accident. For our percentiles, which I'm going to have to figure out what that is. And then quartile 3, we think of that as in the upper 25%, it cuts those in half. So it represents having 25% above and 75% below. So I would actually want P75 here. Okay, so I'm going to have to calculate both of those and then take their difference to give me the IQR. So we're going to go to graph, probability distribution plot. There is other ways to do this. This is going to be the way I choose to do it because I think it's going to be a little bit easier. We'll hit OK. And here I want to find the lower 25%. Ooh, not 27. That would definitely give you the wrong number because that is going to be Q1. And it's going to be down so far I'm not going to be able to see it, which Q1 appears to be 17.76. And then Q3 is going to be having 75% below you. So I want 0.75 below me. And so that's going to be 24.24. So when we look at IQR, that's going to be plus doing 24.24 minus 17.76, and you pull out your handy dandy handheld calculator and you subtract those two and you get 6.46. So that gives you the IQR of the normal distribution, because you can still do those calculations on the normal distribution. You can do them on any distribution, really. Fun times. I'm going to take 8 and make it a little bit down further for easiness of reading. well, easiness of scrolling really. So let's look at some MyStatLab examples. And these are very, oh no, wait, those are coming up in a minute. Sorry. Let's do shortness in males. Sadness. My husband's very short, so I totally understand and feel his pain. So the adult heights of male are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. An adult male is categorized as short if he's less than 64 inches tall. I'm sorry, and is categorized as tall if he's in the top 3%. So let's figure out the percent of males that are characterized as short. So I want to find the probability that my height, I'm using age for height, fun times, right, is smaller than 64 inches on this distribution. And then the other question is about the tall category, and I'll do that in a minute. So I need to change my normal. Let's go to graph, probability distribution plot, probability view. I got to change my mean to match this, so that's a 69 inches. And my standard deviation to match the standard deviation, which is 2.8 inches. And so I got to figure out less than 64. So I want to figure out the probability. So I'm not using probabilities, I'm using x values. So I'm going to do less than 64 inches tall. If you're having a hard time picturing what 64 is as far as height, 60 inches is 60 inches is 5 feet, so 64 is 5'4", which is how tall I am. Fun times. So I'm short for a man. Okay, and that's, not a very big percentage of men. This data was taken from a while ago, though. I believe this is different. It also depends on a lot of other factors, too, such as nationality and other origins. There's some really interesting studies about predicting how tall a child will be based on just the grandparents' heights and the child's length at birth, which is kind of amazing, I think. Doesn't even take into account the parents' height. Fun times. Okay, so how tall does a male need to be in order to be considered tall? So here I'm asking, hey, it's the top 3%. So I'm looking at heights that are bigger than some score that I don't know is going to make, 0.03 because it's 3%. So again, I'm looking for a score now instead of a probability. So I'm going to graph, probability distribution plot, probability view. I'm going to hit OK. All right, and I'm going to do shaded area, and I want probability, and I want the top 3%, so 0.03. Let's hit OK. All right, 74 inches. So above 74.27 inches. If you had written 74 inches, that's pretty acceptable as well. Okay. Alrighty. Shoot, I'm running low on time. I think I'm going to do the examples from MyStatLab as a separate video because this video is now way too long. So I'm going to stop this and then do a separate second video for the MyStatLab ones.